we we decided to do the Intel challenge for Make Ohio 2024. And so to start, we kind of came up with a problem statement and how we wanted to solve this challenge. And so essentially we started with implementing the motors, and we wanted to first get control of the motors. So to do this, we used the Arduino Nano and connected that to our uh, laptop with a few motor controllers. And then we kind of ran into an issue, and we wanted to get, or we needed a bench power supply. So once we got the bench power supply, we were able to get the motors working fairly quickly. And once we were able to control the motors with the computer, we attached them to the stage. So to do this, we got the attachments from the E Club to connect to the motors and as well as the stage. And so basically we have it moves in an XY position, and uh, initially we just implemented a course movement. It moves pretty quickly and not super slow. And once we got that working, we implemented the single step movement. And so we used a joystick. Let me go to the final slide. You can see the joystick there, and we used the joystick to move the stage. And if you want to switch to the single step mode, which is indicated by the yellow light, I don't know if you can see my cursor. Um, when the yellow light is on, it is in single step mode, and it will essentially move one step of the motor, which is about 2.5 micrometers on the stage. And if you want to move out of it, you can simply press the button, and that will move you into the course movement, and you can move it fairly quickly. Um, and so I have a quick video to show to demonstrate that. Are you guys able to see this? For I don't know if it could be full screen.
Yeah, we can see.
Okay, cool. Let me try and full screen it real quick. So there we go. And so this is the course movement right here. And then now it's in single step mode, and as you can see, um it is moving. It takes about 20 steps to go from the measurement of 5 on the dial. And so basically we kind of accomplished our goal with that. And then to finalize it, we kind of wanted to put some data implementation into it. So I'm gonna try and turn the laptop, see if I can get the serial monitor on the screen. But basically, I don't know if this is gonna work, but we have a serial monitor that will it displays the amount of micrometers that it is moving. So if you adjust it, since it moves about 2.5 micrometers each time, it will um, adjust the total displacement since it's been plugged in. And so with that, we kind of achieved our goal for this. We implemented the automated stage. And if we were to go further, maybe it would have some further data implementation or to further expand on the project. And thank you guys for listening. And do 30 days.
Thank you so much. Intel, do you have any questions? The Q&A portion starts now. I will be timing this, so yeah.
Hi, this is Jenny at Intel. Really great job getting to this stage of the project. What was the most challenging part?
So the most challenging part for us was actually implementing the switch between fine-grained and coarse-grained motion. So the push button that we were using wasn't of the best quality, and we had to implement a debounce system in order to prevent it from switching when it wasn't supposed to, essentially. And that took quite a lot of our implementation time.
Hey, hi. Really good job there, guys. This is Hans from Intel. Quick question: were you guys able to do any checks with the slide guide to check any calibration or do any of that? And what were your findings?
We were not able to get to that. Again, our project was more so a proof of concept right now, and the time constraint of the on was pretty evident during the development of this, and we weren't able to do quite a lot of the things that we wanted to do originally, but we were able to get really precise movements. And I don't know if you saw during our demo, but we were able to get micrometer, 2.5 micrometer precision per step, but we didn't do
Yep.
any calibration.
So wait, for the measurement, we went off the measurements on the stage dials. So that's kind of how we calibrated it, since we didn't test it specifically with the slide.
Okay. And did you see a difference with your fine and in the course, when you made those step movements in terms of when you repeated them, what the accuracy of that looks like
It was
or repeatability?
accuracy and repeatability. Again, we actually didn't implement anything as far as like calibrating it, but
Okay.
so over time, yes, the stage could move based on differences in the stepper motors, and it could go like leave its origin point essentially when it's supposed
Okay.
to be up. And we did not implement any checks for that.
So this
Sorry, go ahead.
this leads me to my final question. What are some of the next steps? I think you kind of started to go into that. If you allow more time, or what would you be looking at next to do?
Automated movement. This is sort of just like again, a manual proof of concept. I mean, a switch button is never how you fabricate silicone.
Okay.
I think further, some of the inaccuracy comes from we didn't secure the stage super well to the piece of wood we have. So
Mhm.
it can maybe shift a little, which would obviously throw off a little bit of the accuracy. But then, yeah, I think as far as software goes, it'd be cool to implement it further with software.
All right. Thanks, guys. Good work.
Thank you.
Thank you.
Perfect. Awesome job, guys. Thank you so much for that presentation. And thank you, Intel sponsors, again, for giving some amazing questions. Next up, as I think I messaged Team 80. You
Yep.
guys are up next. Feel
Alrighty,
free
am
to share your screen. We will get started. We can honestly get started as soon as you want. Intel people, are you guys ready as well? Actually, we'll wait a couple minutes, making sure the Intel people are able to finish up their rubrics. Just let me know, send me a message, or even talk. Feel free to unmute and talk to me if you guys are done with your rubrics for the previous team.
I think we should be good because we're gonna kind of keep track, and then after we'll get together offline, and and then submit something. So I think we should be okay to move on to the next group.
Perfect. Okay, perfect. Sounds good. Team 80, whenever you're ready, I'm going to start a 4-minute timer, and feel free to get started.
All right, so we're Team 80. Our name originally just started as the acronym AKEHG, which was just a kind of random assortment of letters that was on my jacket from that I had. And then we kind of put in an acronym that filled it, which you'll understand later as to why we picked this one, which is the Arduino Killers Electronics and Hardware Group. So as was mentioned before, the overview for the project that we were doing here was to make a precision control movement system for the platform to be able to control very precisely how much it moves in any certain direction. And so as we were reading and learning about the project, a lot of the stuff we've seen previously had talked about using flexible connections and to use the flexible connections to adapt for the moving in and out of the precision axes as you twist them. And so a lot of that adds in a lot of kind of imprecisions that can happen from either the material itself twisting or whatever kind of gaps you need to have in order to allow that movement can cause some kind of more and more imprecisions. And so our goal was to try and make a system that would be able to do the movement while staying completely rigid. And so while doing that, we also ended up trying to make a system that had 2 different gear ratios. So you could control coarse and fine movement by changing the gear ratio itself. And so overall, to do that, we made a kind of what our idea was, but basically we were having this 2-stepper motor carriage system. So essentially it attaches to the platform itself, and there is a stepper on the bottom that is linked to a screw axis, and it has 2 guide rails on the side. And that system connects to another carriage that holds another stepper motor that has a spinning gear on the top that connects to a gear that's around the precision axis. And so as you twist the stepper motor with the gear, it turns the precision axis, moving it in or out. And as you twist that, it will move the screw on the bottom at a same rate so that the carriage will maintain its distance within the within the gears. So the gears are always interlocked. And then on top of that, for the gear we made, it actually has 2 different sets of teeth, one on the outside and one on the inside. And so by changing that radius, you're changing the gear ratio, allowing for coarse and fine movement. And that can be controlled by just moving the screw axis while the gears aren't in motion and allowing the teeth to slip through, which we made a quick little kind of SolidWorks simulation of what that looks like. Try and get a good view. And so you can see the moves in with the screw, and then it's able to twist with it. And then we don't have it simulated, but it's also able to push forward to the inner one, and that will mesh with this inner row of teeth, allowing it to move at a slower rate and more precision with the controlling. And so that was our idea that we had, and we had to start working on. However, we ended up running into a lot of problems, as you can tell by our team name. Probably the most major one was the fact that the tables we were working on were metal, and we kind of forgot the fact that a lot of Arduinos have metal on the bottom. And so we ended up frying 2 of the Arduino boards we were using for the project. And then on top of that, for 3D printing out the components, the printers that we were trying to use in the makerspace weren't working. And the one that I have privately that I was using at my place was being not precise as I was hoping it would be. And so some of the parts didn't come out as we were hoping. And then, as I mentioned, what was mentioned earlier was there were some issues with the power in the stepper motors, and since we were using 4 instead of 2, we definitely felt that a lot worse with the power draw, and our power supply that we ended up getting also eventually stopped working, so we had to spend time fixing that. So overall, we didn't ever get like a fully functioning system, though we do have a quick demo that we can show here. So make sure everyone can see.
Could you make sure to speed this up a little bit? You did
Yep.
go a little bit past the 4 minutes. I'm sorry. I
Yeah,
know
we'll
you want
just
to
show
still show
this.
your demo.
And we'll be done. So we have the platform here, the stepper motor with the gears, and when it spins this gear, and then it can move to the inside and spin at a very slow rate for precision movement.
So we're seeing your slide right now. I don't think if you're showing an actual.
It was on the camera. Sorry. I don't know if there's a way to make the camera larger, but it's on the camera for the.
Okay. Yep.
Thanks. Yeah, here, I can stop sharing on here.
So what I did is I allowed multi-pin, so you should be able to see both, at least for right now.
Okay, so you can see the camera, you can see the movement of the gear, and then as it moves in, it's able to do the smaller gear, allowing for smaller movement and more precision. So, which is about all we have, and then future steps we can talk about if able to, but we're kind of running out of time, so. But basically implementing the full actual hardware system and making the software be able to keep all systems in line with each other would be the kind of next future step.
Hey, great job. So you mentioned about the simulating on AutoCAD. So was that anything helpful in simulating the flow, like the coarse movements? Were you able to do that?
So we were using the SolidWorks mainly just to confirm all the parts would be fitting in together and like kind of the gear ratio of how much it would move. We haven't been able to like confirm how much the difference is between the coarse and the fine movement, just because we haven't been able to do the actual test and see like how much per turn moves in and stuff like that. And we were going to use sensors to try to help us track the movement, but then our Arduinos were not functioning, so we weren't able to get all of those hooked up. So for now, the CAD was mainly just for getting everything in place and getting us a good idea of what we were trying to build.
Okay, great.
Hi, this is Dan from Intel. The question I have was, what led you to deciding to do the gear ratio versus the fact like a stepper motor is designed to have very fine control? Why did you choose to go down the gear ratio path?
Yeah, so one of the big reasons we kind of wanted to do both the gear ratio is because, as you mentioned, the stepper motor has the function to be able to finely control individual movements. But since we're working on such a very precise scale, we figured it would be good to have two different areas where you can, as you're trying to adjust the base to match the images or whatever else is going on to try and get it to move to the exact spot you need, being able to both move it at a consistently fast rate, but also in very precise movements. We figured that would be something that would be helpful in the future for making software, like pretty much making life with software and a little bit easier to
Awesome.
like write code for.
Got it. Thanks.
So these, one question on the tool used. So these were part of the kit, and you had something else as well. This was not the standard kit provided, right?
So most of what we used came from the standard kit, and then we as a group just had a couple of maker kits on our own individually that we brought in for the extra stepper motors. So the stepper motor, we have two stepper motors, but we're only using one here, which is the one that came with the kit. And other than that, the only thing that wasn't with the kit are the gears that we printed out we made it in SolidWorks and then printed it out in 3D printing.
Okay.
So you started to speak to kind of what's next. Maybe you can kind of walk us through a little bit more details of maybe some of the additional things you're going to need. To Dan's question, you kind of took a little bit different path to integrate some additional things into your design. So maybe if you can tell us about where you are now, what are some of the other things that you're probably going to need to design, build, manufacture to be able to get to that end product that you're looking to get, from your SolidWorks design that you showed.
Yep. So
just from the software perspective, we have what we need. We just need to have a huge integrated piece because a lot of the problems that we're running into are speed and latency. So we would need to have an Arduino that's capable of running all four motors so that we could integrate all the software that way. And then in terms of hardware, we just need to get the electrical components working.
Yeah. And then, like you mentioned, building like the actual harness that would hold all the components together. And then the only kind of software then that we would have to adapt really, rather than like we already have a base for it, we would just have to adapt it for what would happen in real life is the connection between how much turning the gears affects how much you have to move in and out the screw axis in order to keep those two gears meshed together properly. So that's the only thing that we would hopefully be able to test in real life once we had the full carriage and such built.
All right, thanks. This is good work.
Thank you.
Yeah, thank you, Team 80. Good job.
Perfect. Thank you guys so much. Your project was really incredible. Next up, I think I did message Team 76. Team 76, are you still here?
Yep, we're here.
Perfect. Are you guys ready to share your screen? If not, we do have a little bit of time, but we'd love to get this up and rolling.
Yeah, yep, I can get on that.
Perfect. Thank you so much.
So we did the Intel challenge just like everyone else here, and our approach to it is, there we go. We decided to also go the gear reduction route, but rather than using gears, we use discs with inelastic like string in between them to prevent backlash or any like drift within the two shafts. So we use like the provided parts of the linear stage, the stepper motors, and we use the Arduino Nano to control those. And then we have all of our custom parts, which are either Delrin. So like the white parts that hold the motors on are Delrin, or the main black column is all machined out of Delrin. And then we have an acrylic base, and the wheels that the string wraps around are 3D printed. To fabricate these, obviously, like we 3D printed all of like the pulleys, the acrylic and Delrin was all machined on like a mill and a lathe and stuff. And then everything like that is just off the shelf parts such as machine screws and springs, stuff like that. For our cost, everything that we used was kind of just out of like scrap. So it was pretty much free unless you count the stuff provided in the kit. So for our iterative design, we went through multiple designs of pulleys, experimenting with shallow grooves, deep grooves, experimenting with how the string is going to stack on itself and how that affects the smoothness and speed of everything. So what we ultimately ended up with, like on our final system, is a mix of deep grooves on the upper pulleys that you can kind of see here, like this blue, and then shallow grooves on the lower pulleys to allow the string to pass over itself easier. And then we also messed with different ideas for tensioning. So like we had a crude initial thing of like a hair tie, and then eventually went to some springs. And then we experimented with some stainless steel wire or fishing line, and we ended up on the fishing line because it was easier to spool up for us in between taking it apart. So I'll pull up our video here. That gives a little bit of a demonstration, if I can get to it. There we go. Okay. So this is us moving the stage 1 millimeter in one direction and then 5 millimeters in the other direction. Hopefully it's not green. There we go. So the blue wheel will move 1 millimeter, which is 2 full rotations. As you can see it doing here. And then the red one will move 5. Or 3, not 5, sorry. So that's our design for that. And with this design, we were able to get a calculated precision just from how many steps to, you know, how far it's moving, that we measure in millimeters and everything like that. So for 1 millimeter, it's 2,572 steps, which then led us to a precision per step of 390 nanometers. And then that test that you saw in the video, we repeated multiple times, and every time it was very consistent, getting right to the exact same point. For our future improvements, we could add an encoder to the actual like shaft of the micrometers to give us like a closed feedback loop, so you could adjust position if there is error within it. And then we would like to get the intermediate steps on a stepper motor working. So like if you were able to do half steps, you could double your precision. You could also increase the diameter of the top pulley, increasing your gear ratio, which would increase the precision. And then we would like to reduce the size of the whole assembly, make it more compact, make it out of a common, probably metal, so it's a little bit more rigid, even though we use something like Delrin, which is pretty rigid. And that would like aluminum would work pretty good for that. And that is all we have. We are ready for questions.
Hey guys, really good work here. The one thing that wasn't first question I have wasn't too clear to me. Your two different motors, are they moving the same axis or is it X and Y? How is that?
Yeah, so
What
the two
maybe you
different
can-
motors are moving the two different axes and they can operate independently of each other. So if you see in our prototype, this motor drives the red wheel, which
Okay.
we call the y-axis, and then this motor drives the blue wheel or x-axis.
Okay. But during your talk, you mentioned that once moving, there was a correlation with the revolutions, you know, with in terms of fine versus like a course between the two wheels. That maybe that's why I got a little confused.
Yeah, so to like calibrate, we had to find the relationship between steps in our drive and the movement of our stage. So over the course of moving different distances, we found the relationship between motor steps in our system to the rotations of our micrometer.
Okay. And you mentioned, in terms of with the next steps, redesigning or maybe making it smaller. Can you talk a little bit more about that? Because the current design, maybe you can tell me like the size of it. That looking at the height, it looks like I don't know. And what you perceive you'll be able to miniaturize it, after you do that. What will be the new size, roughly the dimensions, XYZ, if you will.
Yeah, initially we made it so tall to reduce the impacts of these wheels moving in and out on our pulley system. Like as you went from one extreme to the other, how far that distance would change. But as we got further into testing, we realized that was not as much of an impact as we expected. So we could move these lower drive motors up to like right next to our like micrometer wheels, as well as turning these motors the other way so that they would almost sit under the stage. Both of those would like dramatically reduce the size of our system.
Within that, you could also make the tensioners in different spots. We just have them mounted in like a easy, like convenient spot. You could put tensioners in different spots and pretty much reduce the whole footprint of it all to essentially just the dimensions of like the stepper motors, just butted up on a corner, and that would be pretty much your whole footprint.
Okay. The other thing too, when you're doing a demo, I'm not sure if I saw the stage move at all. Is your stage actually moving when you run the different motors, the different axes?
In the
Yes.
video,
Yeah.
yeah. So the stage moves. You can kind of just tell by the like tried to record more of the micrometer because then you can kind of verify like it's actually moving 1 millimeter.
Okay.
Yeah, it might be hard to tell in the video like that 1 millimeter movement is kind of small, but you can see the micrometer spinning and the actual reading on the micrometers.
Okay. All right. Thank you. Good work,
Yep.
guys.
Thank you.
This
Hey,
is Jenny at Intel. I just have one quick question. You mentioned the fact that you used mostly free scrap material.
Mhm.
Why do you think it's important to drive a low cost solution for this particular project?
Well, cost, like in industry, cost is everything. If you're prototyping and like, your prototype is going to be crazy expensive, your prototype's just not going to get built. Cost is a extremely important variable when like you're prototyping anything and final designs, especially if you're going to make it at scale. Like if you were going to make this out of whatever, titanium, that'd be extremely expensive and you're not going to make it at scale compared to where, you can just make it out of like machined aluminum and you can scale that a ton or plastic or whatever.
Great. Thank you.
Awesome awesome job, guys. I'm sorry, my fault. Awesome job, guys. Way to go! Incredible presentation. Next up, we do have Team 36. Team 36. If you have your materials ready, feel free to share, and you can get started whenever you want.
Right. Um, so you want to explain it?
Yeah, sure. So for our project, we have the two. So basically, we're gonna have a laser come down from the top of the box. Then we're gonna have two magnifying glasses that control both the X and the Y axis in order to make the laser coming down more precise.
And then we used two amino and second lights for the
We can't hear you well. Can you come closer to the mic?
sorry. We used the stepper motors from the Intel kit as long as the motor drivers, and we use a Arduino Uno to help us, and we basically just made the motors like rotate each of the magnifying glass. One does like X, Y, and one does X, one does Y to make it more precise.
And then we also use the ultrasonic sensors. So whenever the ultrasonic sensor here, and then whenever the magnifying glass moves, we'll be able to tell if it's moving the direction and how much we want it to make sure it's precise and accurate.
And then
Yeah. So it's a really early stage right now, so we were kind of stuck on time. We were trying to make the top magnifying glass move, but we only managed to get the bottom magnifying glass move. But we were able to get it to move the laser back and forth. And given more time, we would probably use a universal joint. Here, do we have like a picture of it? Anyway.
So if we have a slide with the picture.
what?
So
You join.
I don't think we can hear
Yeah,
you.
I'm
We can't
sorry, we
really
can't
hear you
actually
guys.
hear you.
I'm sorry. So at the very beginning, when we were trying to measure the precision of a laser hitting a specific target,
It's
We're
still
really
low.
having it difficult to hear. I don't know if you can move the mic closer.
not really. It's kind of just really loud.
Yeah, speak up.
All right. So, all right.
Much better.
Yep, better.
Yeah. All right. Sorry. So we have at the very beginning when we were trying to create basically this big box that has two magnifying glasses with lenses to refract light. We were trying to figure out how to actually move the lenses. So at the beginning, we're like, okay, well, let's just have like two rods, maybe rotate, and then it will just have this nice 360-degree movement of able to rotate around. But then we first came across the problem of, well, if you just have these two rods sticking, one is perpendicular to the other, so nothing's going to move. So our first solution was thinking of using a U-joint, which would have moved it around a lot, but because of friction, you would lose that precision and accuracy if you wanted to scale it more down, or if you wanted to, or just in general, you're just going to lose more and more accuracy and precision. So that was out of the question of using a ball bearing. And then later we had the idea of instead of connecting the two, we just use two separate ones. So you can have one that has a more accurate reading for the X and then the other one for the Y. And then later we had also we also use the sound sensors to have, we were going to use the sound sensors to have a better accurate reading of when the magnifying glasses were to
basically rotate to see if they were in the correct location, because human error is always a problem that we have to deal with. So we wanted to make it as automated as possible by having something to sense, hey, you're going too far this way, hey, you're going too far this way, and to auto adjust to it. So using a some type of thing to sense how much it rotated would allow for that human error to be removed. Another thing that we thought about doing, because we want that precision accuracy of the laser hitting the target, is maybe using vibrations. Of course, that didn't come out because that didn't really come to play at all, but it's a notable suggestion that we had. As for the project itself, I'm just going to take a little tour of what we have.
Hey guys, sorry about that. I know it's been 4 minutes, so could you please I mean, I know you're producing your product, that's fine. Feel free to wrap it up though, just a little quickly, if that's okay.
Okay. So right here is just the breadboard with the second. And then up here we have the laser. Down to the top and with the sensor on the
We
side.
really can't hear you again.
I was a little bit closer to my face, but it's causing
Still not clear. We can't hear you.
right here we have a sound sensor.
Guys, I'm really sorry, but unfortunately the mic quality is it keeps cutting out and we're not unable to hear anything. I think they might just have to go off the video. However, if the judges would like to take some time in their question, they can start to ask more about the actual product. I'm sorry about that, guys. Could you, I think it was working better if one of you was talking at once. I don't know who, but I think if one of you is talking, it works way better. So could you try to implement that for this Q&A session? That way we at least have a little bit better time hearing you when the judges are asking questions. Thank you.
Yeah, if you wanted us to, I could join on a different computer if that'll be more helpful.
I'm not sure if we have the time right now, unfortunately.
right.
You can try it and we can maybe push you on to later, but I think for right now, let's see with what you've shown, let's go over, you know, how like your product and everything.
All right, got it. So yeah, we can start taking questions.
So one question that comes to mind, if maybe you can just tell me, you know, generally, the decision around incorporating, there's quite a bit of different components in your design, right? Optics, laser, sound, etc. What made you decide to go in that direction? You know, based off of, you know, the description that was in the challenge, and then the amount of time you had, you know, etc. What made you decide to go and take that path?
So first of all, we were thinking about using vibrations and things like that, but we didn't really have the materials, or we didn't know what we could use to do the vibrations. Well, we did know that we were able to go to the store and get magnifying glasses. And so that's how we decided on doing the magnifying glasses. And then there was another option where we could use the universal joint. But once again, we didn't have that at our disposal because by the time we got to that point, it was already pretty late and everything had already closed.
What did you find most challenging about this project?
Basically just trying to figure out a lot of the like basics of a lot of the parts. Like I had a lot of trouble getting
Yeah, I'm really sorry. I think it's whenever you speak, for some reason, it doesn't seem to pick up on your microphone. I think just one person should be able to speak.
Let's talk about the motor. I'm sorry, what was the question?
What was the most challenging part of this project for your team?
So this was two of us, our first time like actually working with Arduinos, working with a lot of electronics. So that was a big task for us. And We were also trying to get the motors to work the whole time, and
Stuff.
yeah, trying to figure out like the wiring, trying to figure out the correct code that works with it. Do you guys have anything to say about that? You have to get closer.
So on the note of next steps, if you have more time, what were you planning to come up with a prototype? Like what things you think would make it workable in terms of next steps?
I think using the universal joint would really help us out because so what our problem was is we wanted it to move in like a 360 direction, but we were only able to move it like in the X and Y directions. And if we wanted to move it like in the 360 direction, it would basically be floating in midair, and we didn't have anything to like hold it down and also be flexible at the same time. So in the future, it would definitely be to use the universal joints to make it like work in a 360 to give us even more precision. And then also we could probably figure out a way to implement the XY stage so we can get like so we could have the fine movements, because right now using like two magnifying glasses and then like a motor and hoping that it's precise isn't a very good method.
Thank you very much, Team 36.
Yep.
Awesome project, guys. Thank you so much. Sorry about the technical difficulties, but I was very happy y'all were able to make it through it. Team 74, you guys are up next.
All right, sweet. Just checking. You can all hear me, right? Okay.
Yep, we can hear you.
Perfect. Perfect. Share my screen really quick. All right. So, as you all know, we were working on the Intel challenge, Michaela and I. And for this, we used just the standard materials that we were given as part of the kit. We used the breadboard, we used the XY linear stage we were given, the power supply and power supply module, an Arduino Nano, two stepper motor drivers, along with their two stepper motors. They are the bigger ones, and you'll see that in a later slide. An ultrasonic range sensor, a wood base, and some wires. So to set up, we connected the two stepper motors directly to the XY linear stage using some 3D printed connector parts that we were given. The motors were wired up to the stepper two-phase ports of the drivers, and then the step and direction ports of those drivers were wired to the data ports of the Arduino Nano. The 12 volts we needed to run the stepper motors was extracted from the power supply directly by soldering to the barrel jack, and then the ultrasonic sensor was connected to the data ports of the Arduino Nano. Here we have some wiring diagrams for the modules themselves of the motor drivers, and then you can see that the labeled parts are connected to where they should be respectively. Some problems that we had when we were setting this up was that the ultrasonic sensor was unable to actually take accurate distance measurements, and so we would like to, in the future, use more precise measurement devices for each of the two directions. And to compensate for that for now, we've been taking them using the stage's built-in measurement tools, the micrometer part of it. Another problem we had was the height of the second stepper motor did not match the height of the arm, and so we created a stage for the stepper motor that you'll see on the next slide. And finally, the last problem we had was we were unable to get voltage for the motors, and so we solved that by soldering to the actual power supply module itself. So here we have on the left a demonstration video of it, and on the right we can see the picture of our product itself. You can see down here the stage that the second stepper motor is on to keep it elevated at the correct height, and then the first stepper motor sits just on the top of this wood base. There are two ways to control it. The first one is that there is or I guess there's two modes of operation. The first is what it's doing right now, which is that it's running through a pre-programmed route to go a kind of back and forth zigzag pattern across the stage to make sure it reaches all of it. And the second is that through the serial connection to the computer up here by the Arduino Nano, you can input the distance that you would like to offset each motor and control it on the fly. What? Oh, and then we have some code for it that we've written. Very simple stuff. Some functions to move the motors. Here's the built-in path. And then down here is where it can either take the built-in path mode or it can take the distances. That's what I already said that. Do we have any questions? All right.
Hi, this is Jenny at Intel. Can you explain, so the built-in path, it looked like you described that as like a zigzag motion?
If you can see my mouse, because I don't have a demonstration of it in full, it's sort of like, I guess it's sort of like this across the stage.
Oh,
So
okay.
it moves one of the axes in full and then moves the other axis a little bit and then takes the first axis back and does that in a pattern.
Okay, thank you.
Good work, guys. Pretty good final product here. In terms of next steps, if you had more time, or maybe even to reconsider your design, what would you do? What would you do different or
Definitely our next
additional?
steps would be try to reduce the cost of this. I know that the stepper motors themselves are sort of pricey as well as the controllers. We did have other stepper motors available to us, but they weren't nearly as precise. So the solution for that might be to use the cheaper stepper motors with an encoder to try and have some feedback loops that way it can correct itself, as well as getting more precise measurement on the position of the axes themselves using, say, like laser distance measurements instead of sound.
And you mentioned a couple of different challenges you ran into while you were doing this. If you could pick maybe one or two, um, some of the really big things that you had to get over, to get you to where you had a finished, quote unquote, finished product that you're demonstrating today.
Sure, give me 1 second.
Which one's each one? I know.
Incredible job, guys.
Sure. Okay.
Oh, sorry. Is there any more questions? My fault.
I was going to try and answer that question. Sorry.
Yeah,
I'm so sorry. My fault. My fault.
You're good. For sure, one of the big problems that we encountered was the actual measurement of the stage itself. Because the ultrasonic sensor is so imprecise, for the most part during testing, we tried to just measure it using the micrometer on the stage itself visually, since it has markings indicating how many steps it's gone through.
Okay. Did you guys get to test around with the slide guide at all to check that, or did you do any type of calibration as well?
We did a little bit with the code. Yes, we tested out the code to make sure that it could move it a specific number of millimeters and such, just visually again. We didn't get to use the slide thing because we couldn't find it.
Okay. Good job, guys.
Thank you.
Thanks, team.
Sorry about that. Incredible work, guys. My fault. Next up, our final team, but certainly not, in no particular order. We have team 97. 97, are you guys still here?
Yep. Hello.
Perfect. Hi, nice to see you guys. Feel free to start sharing and go through your slideshow whenever.
Hello. We are Team Dr. Vivek's Extra Credit, named after a professor who got us into the MakeOHI. And this is our approach to the Intel Challenge. My name is Junlo Galbo. I'm a second-year electrical engineering major.
I'm Helena Trilienza. I am also a second-year electrical engineering major. And we had another teammate, Will Vidito, who is a second-year material science and engineering major.
During this meeting, we're going to talk through our process to the design. Then we'd love to show you the demo of our working stage. Afterwards, we'll go over some lessons learned and as well as what steps we plan to take in the future with this design. Overall, our process, we decided to break down the challenge into the smaller pieces.
Your voice is breaking up a little bit. It's just a little digital. I don't know if you're not close to the mic or.
Can you hear me now?
Yeah, we can, but you're sounding a little digital. I don't.
I'm not sure how we can fix
Yeah,
it.
when you talk, it seems better. I don't know if it's just the position of the mic.
Oh, maybe it's on this side.
Can you hear me now?
Yeah, much better.
Okay. So we decided to break down the project into smaller parts so that way we could tackle each individual step. We need to figure out how the components we were using are functioning. We needed to figure out different design ideas to handle it. There were certain challenges presented, like by the fact that the stage, one of the axes that you can twist, the micrometer, moves along with the stage as the other rotates. And so there were various design considerations that we needed. After we learned more about the materials we were working with, we decided to create some CAD models for mounting and design some code to work with these motors. Afterwards, it was implementing the design, testing, and making small tweaks to refine as necessary. As you can see here, we started looking at the schematic of our motor driver to figure out how exactly it works. We designed a very simple motor mount that could be injection molded with plastic for mass production as needed. And we ended up deciding, although we considered multiple other things, we decided on a rail system. So that way the other motor could slide in the X and Y direction, or in the Y direction as needed, to accommodate the movement of the stage. And now we'd love to show you a demo of our project running. As you can see, with the use of the analog joystick, the micrometer starts to spin, and the stage gets pushed very small amounts in one direction. By moving the joystick in the other direction, the other motor begins to spin, and the stage once again moves in very small amounts. This can be adjusted programming-wise to follow a precise predestined track, or the joystick can be used as a course adjustment to position the stage where you want to begin.
So during this project, we learned how to collaborate on creating creative solutions. We also troubleshooted issues with connecting components and coding. This was actually my first time using C with Arduino. And we also faced issues with the building process, as mentioned, with the X and Y directions. We had multiple ideas, such as using the rail system, flexible tubing, gears, or a track system. We also learned how to make our designs come to life. In the future, we would like to make the motors more stable and test different designs to see how the methods affect precision. We would also like to use heat sinks on the motors. At some points, they're a little too hot to touch. And we would also like to find maybe an alternative motor to these because they need 12 volts minimum. And we think that other options should be explored to make it more accessible.
Swinging it back around to the relevance of the project and specifically the accessibility, we wanted to make sure that our design could be that kits could be manufactured cheaply and sent out cheaply, so that way we could have the widest reach possible. So anybody who wants to get involved with micro making and testing out would be able to start doing so and experiment with that. We also wanted it to be as user friendly as possible because of this. And so we used simple C programming language on a very commonly accessible microcontroller, the Arduino Uno R3. And additionally, we were hoping that this sort of product would be able to help bring people together in exploring micromaking, which is currently a little bit of a prohibitive field of electronics to get into. So hopes that our design could be made cheaper, especially with mass production, and that kits could be sent out anywhere would greatly increase the who has access to micromaking. And that's all we have slide-wise. We'd love to take questions.
Good work, guys. Yeah, really, thank you. And it's good to hear that you're, as you were designing and making your final product here, your prototype, you're considering something that will be a lot more accessible to almost anyone that want to, test or play around with this even at home potentially. The first question I have is, um, during your talk, you mentioned, with the joystick and moving. Did you do anything around the calibration so that you know when you make a certain amount of movement, it's precisely so many, millimeters or whatever? Did you consider that?
Yeah, we did. So we actually set it so that it would have a small step count. So the step count is around 10. So if you push it to the left so many times, it'll move that much, 10 steps on the motor.
The motors
Okay.
themselves have a step count of 200 per revolution. And so
Okay.
considering the fact that the micrometer knobs are 50 microns in size, you are working on the micron scale with that adjustment. That was our main method of determining how precise we were. We didn't have a whole lot of time to design more extensive fine adjustment features. We ran into some trouble with a faulty motor early on, as well as some delays in getting our motor mounts manufactured because we were 3D printing them. One of them actually snapped, which is why you can see one of the motors is currently zip tied down. We hope that some sort of injection molded part would be sturdier and able to be more rigid for any final product.
Okay. And for that, that's the step count and the precision of the movement. Where do you account for that in your code that you wrote? Is that how you were accounting for the movement so that you know the precision?
Yes, we were largely relying on the step count of the stepper motors.
Mhm.
Our code was specifically written to be accessible. It's supposed to be very easy to tweak as needed. And the hope being that in the future others can program in C with whatever setups they're going to need for their micro making.
Okay. So my last question, it's kind of two-part. First, what are, given more time, or what are the next things you'll consider to do, the additional upgrades, et cetera, right, to improve on this? And then second, what's the next step in making this more accessible, to your point, right? Your last comment in your talk about making this so it's available for anyone to be able to use.
Yeah, for sure. I think design wise, we would like to find some kind of like flexible tubing or rail system that could be easily manufactured. That way we could include it in a kit, so you wouldn't have to scrounge for those parts.
Once again, when we were running these motors, we found that they heated up a lot to the point where they were too hot to the touch. So we could either explore adding heat sinks to the motors or look for motors that can run on lower voltage that are less powerful, less likely to heat up that much. Accessibility wise, we kept our making strategies pretty bare bones, minus the 3D printing. We mostly used hand tools to cut out our parts design. We used a couple screws. As I mentioned a few times, we wanted our designs to be easy to manufacture, mass produce, so that way they could be used in this kind of kit, because the lower the price is, the more accessible this kind of technology is to anybody who wants to begin exploring this field. And so by using common microcontroller, the motors, I don't remember the exact price, but they're not too bad. They would be included with the kit. And the stage, if we could add in a little bit of infrastructure, I guess is the word, to make sure that everything's sturdy, stable, and connected. And if that infrastructure can be mass produced, then it can really bring down the cost, which increases the accessibility.
All right. Thanks, guys. Good work.
Thank you, team, for 97.
Awesome job, guys. Thank you to all the participants, and thank you especially to all the judges for taking time out of their busy schedule, busy days to talk to you guys. I saw some incredible projects here, and I can't wait to see what happens in the future with these projects. I can't wait to see, what new stuff you add to these projects. Thank you so much for attending Make Ohio. We'll obviously get back to you with more steps, more details later on. You guys did incredible, and you should all feel excited and very happy about yourselves. So can't wait to see y'all later. Have a great day. Feel free to drop off the Zoom call as well.
Hey, thanks again to all teams for taking some time to take on this challenge. Thanks, guys.
Thanks, everyone. Great work.
Great work, everyone.
Thank you guys very much.
Of course. Feel free to hop off the call. No need to stay on, and we'll get back to you with more details. Okay.